So yeah, so welcome everyone. Today we're gonna be discussing or tackling the syntax analysis um, topic. Also, a small recap of the last session. If someone wants to recap the last session in the compiler session. So we did what we call lexicon analysis, right? So could anybody is anyone willing to say what was the end result, and what was the goal of last session? Anyone?
Um, I'm not good at summarizing, but we looked at how to make a lexer and how to tokenize maybe an expression, read tokens, and see if the expression is valid or if the tokens are valid.
Okay. And so the objective of last session was to implement a lexer, right?
Yeah.
Okay. Yeah. So a lexer is uh, going through all the tokens, going through all the input and um, generating tokens out of it. Transforming it into a set of tokens. كل token and the token type. You did that exercise as well. Identifier ولا literal ولا its own type. Now we're at the next step. Now that we have this set of tokens, what can we do, or what can we do to to reach the end result ديالنا, which is and in the end to generate an executable, right? So that we can execute it and run it in our computer. So yeah, the logical extension the last session is today's session, which is taking the output of the lexer and feeding it into a parser. The parser, on the other hand, will spit a different kind of data structure, which is in the form of a tree, which will give us information about the the which will ease the meaning, will retrieving the meaning of the semantics of the whole code that we have. And this is one of the reasons why we're doing it. Yeah. So the outline would be that we'll start with a small introduction, motivations why we're doing this, and then we'll talk about context-free grammar. Anyone familiar with context-free grammar? We will cover it in this session, so it should be fine. We'll have a few basics. We'll try to cover a few basics, and then we try to use that grammar to build, or we try to define a grammar, and then we see how we can use parsing techniques to to apply that grammar to our input, which is the source code, or which is the tokenized source code. And then if we have enough time, we'll go through the implementation. Otherwise, we will just see snippets of it. So as we said, this is the step where we are right now. We are at the syntax analysis. We have a set of tokens. We're trying to generate an abstract syntax tree. Um, Anyone who knows what an abstract syntax tree is? Yes.
I think it's a representation of the code um, in an abstract way, which means it's represented in the memory, and it's just like a translation of the syntax that is written in characters to another form, which is like a tree that can be traversed, I think.
Okay. Anyone else? Okay. So yeah, I mean, you're right. I mean, the syntax tree is something that looks like this. Um, syntax tree is something that looks like this. It's just defining the conditions, or defining the structure of the code itself. It's representing it into a tree structure, which helps us first بدأ we can check the correctness of the syntax easily. ثانيا we can define hierarchical structure to be representative. مثلا every node هنايا, the root node is representative of the whole source code, and then as we dive deep into the logical parts of the code, we branch into multiple places of this syntax. So it's helpful to understand and to retrieve the semantics from this syntax. But in itself, مازال ما درنا والو في syntax tree. We just define this into a tree structure. We say that, for example, هذا الكود that's displayed in the example, if x is greater than 5, then x equals 1, then assign 1 to x, else assign 0 to x. We're just trying to translate the source code, which is like this, into a structure that is easier to work with further this sequence or a series of operations that we will do. Code optimization, for example, it's better to have a tree structure to be able to do optimizations easy, and we'll see that in the next chapters. Yeah. So we can talk about context-free grammar. So for us to be able to define a language, for us to be able to define what is correct in a language, what is syntactically correct and what is not, we need a set of rules. We need to say, for example, if I need a condition after it, I need some statement that is that should satisfy a few rules. And one way to define those rules, programming languages عادية, is context-free grammar. It is one of the most common ways to define the rules of a language, the grammar rules of a language. And when we talk about grammar now, we talk about the syntax. What is the set of correct statements that are part of this language? Anything that is outside, we consider it to be false. So we need a way to define all the set of statements, all the set of ways that we could write the language. And one of the ways is this, as I said. So had the context-free grammar فيه terminal symbols, I think we saw them, tokens from identifiers, literals, etc. Any non-terminal symbols, and those are bحال variables, we can use them to represent one or more terminal symbols and combinations of them. There is a set of production rules. We say that one symbol is equal to another symbol, and then there is the start symbol اللي هو اللي كنبداو منه, let's say the root. So one common notation here, the Bacchus NOR form, and probably, whoever studied the compilers class would know BNF. It's the most commonly used notation. So it says it has a few small rules. So the non-terminal symbols are enclosed in angle brackets, halaka. So when we see this, we say, okay, those are just non-terminal symbols of the grammar. They are not identifiers or terminal symbols of the language. And terminal symbols are written كيف ما هما. If we have identifier, we write ID or identifier, plus we write the operator itself, etc. And we have this epsilon. Epsilon means no character, BNF. It means that we have no character. It's empty. And we see how we can use that. Production rules are assigning what's on the left-hand side, which is non-terminals to what's on the right-hand side, which could be either terminals, non-terminals, or combinations between them. And yeah, this is what's on the left and right-hand side. And alternatives are separated by pipe. And this is an example. Let's define an initial statement or statement, which could be ID equals expression. So this is a simple assignment. What's on the left-hand side of this assignment هو the ID, and what's on the right-hand side is expression, which is a non-terminal, which also evaluates to either ID or a number. And a number is one of the numbers, 0, 1, or 2. Any questions so far? All good? Okay. Yeah, Abdelghafour?
Yeah. Is anything under the angle bracket should be tokens, right?
Sorry, are you talking about non-terminal
Yeah.
symbols?
Anything enclosed between the angle brackets should be tokens, right?
So, I'm not sure what you mean by token. The tokens with the token types we defined last time.
Yeah.
Yeah, the tokens that we defined last time, Huma had the terminal symbols. One of the things Huma had terminal symbols. Al ID stands هنا for identifier.
Yeah.
It's one of the one of the symbols that we defined. Identifier, literal, token types that we defined last time are part of terminal symbols. So هما terminal symbols alongside operators وهذيك الابسيلون, which is a special thing.
Yeah. Thanks.
Okay, cool. Any other question? Okay. With that said, there are a few problems with grammar, with context-free grammar. This example is I think very simple. It doesn't show the complexity of grammar. ولكن grammar could be very complex and is usually in real in programming language cases pretty complex to write. Look, a grammar could be ambiguous, and we talk about special cases of ambiguity that will lead to special cases of problems that we will have to solve if we decide to go with a specific parsing strategy or a parsing technique. And I'll talk about this later. I wanna mention this quickly. So one of the ways that grammar could be ambiguous is if it allows to generate multiple parse trees for the same input string. So if you have the same input string, let's say A plus B times C, the grammar is ambiguous if it allows you to generate, if it is inconsistent to generate the parse trees. So in this case, you can see that you can either fall within the first case, اللي هو تسبق the plus the first iteration, and هو اللي يكون عنده precedence over multiplication or العكس, because the grammar is ambiguous. If you read from the left side, you will prioritize the plus, and if you read from the right side, you will prioritize the multiplication. And this is a bad example. Usually, a good grammar is a non-ambiguous grammar. And there is one thing that is said is there is no such thing as ambiguous language, but ambiguous grammar. So the definition of the grammar هي اللي كتكون ambiguous that leads to ambiguous explanations or interpretations. Yeah. So one of those is called left recursion as well. So left recursion, and we'll see in top-down parsing. Left recursion occurs when a non-terminal um, derives itself as the leftmost symbol in a production rule. So what we mean is the the non-terminal that is being um, on the left hand side of the assignment finds itself somewhere on the right hand side of the assignment as well, and it leads to some kind of loop, which is an infinite loop, and this will prevent the parser from functioning correctly if it reads from the left side. Because now in this case, imagine you have something like this, and expression is equal to is assigned to x, is evaluated as expression plus term or term. If you read from the leftmost, you can keep assigning to expression in an infinite loop without being able to exit, because it's always true. Expression is expression. And to break this, it's better to try to avoid this by eliminating left recursion, by factoring out the common prefix to take it in another expression, in another production rule. And the solution is here, the example on the bottom, it's trying to solve the problem by defining it into two expressions. Expression is term expression 2, and expression 2 is either plus term expression 2 or an epsilon. So is this example clear? Okay, cool. eBNF is an extended version of BNF, which adds a little bit of functionality, a little bit more functionality to the mix. Okay, we have a few more expressions that we can use. One of the most important ones regex, like syntax is inspired from regex. Star for 0 or more, plus 1 or more, question mark is 0 or 1, and use of parentheses to group statements with each other. And if you apply those, you'll end up with something like this. Or if you remember the language or mini language, mini Python that we wrote last time, or we can choose a language we can choose a name for the language in that. But this is maybe a set of this is the definition of the grammar per se, or simple description of the grammar. So now the statements is 0 or more statements. Let's use lang. Yes, I agree with that. Let's call it as lang from now. So the root is statements, which is 1 or more, or sorry, 0 or more statements. A statement could either be an if statement or an assignment. An if statement is if followed by an expression, then followed by statements. Else could be there, could be absent, depending on the context, and so on. This language is pretty similar. This is maybe a bit simplified. It doesn't have everything, because this is just for the sake of understanding the context-free grammar. But yes. All right. Questions? Yes, Nizar.
Can you give an example of left recursion? Maybe one where I understand it sort of in theory, but do you have like an example where we would have left recursion?
Would the man example a real world example?
Maybe, or just something more concrete.
A left.
I know.
Mm-hmm. Yeah.
Sorry, I know it can like go infinitely, but I've never seen it.
Okay. So here it depends on the implementation. It depends on the parsing algorithm that you're using. ولكن غالبا it the decision of using واحد the parsing algorithm is gonna force you to try to solve هاد left recursion or not. Let's say we're gonna see the parsing algorithms later. If you decide to go with a parsing algorithm that is top down or recursive, for example, let's see. We're trying to go with recursive descent parsing. It's going top down or leftmost. You're evaluating statements من the root down and from the left statement to the right statement. So if you encounter a case where you have مثلا هنا instead of statement if statement we have statement, you could stay in the loop forever because you can't go out of it, because you always try to match the available expressions, so you always match the one that keeps you in the loop. So you'll never get to how can I say, you'll never get to evaluate the syntax correctly because of the way the grammar was written, ماشي because the grammar is not correct, but because the ambiguity was there, that and the algorithm was not expecting that type of ambiguity. So it's multiple, how can I say, it's multiple decisions together. So
Understood.
if you go with a way to write the grammar, or if you go with a way of implementing a parser, you have to accommodate for هذاك parser by defining your grammar in a way that doesn't create conflicts or that doesn't create inconsistencies. And yeah, this is something to worry about actually. So, yeah, thanks for the question. Yes, Smithy.
Yeah, هذيك الستار اللي كاينه من مورا ستيتمنت واش is it there to eliminate زعما the recursion infinite recursion؟
I had if statement.
لا الأولانية statements.
Sorry, I had a statement.
statement اللي فوق منها.
Yes.
The star اللي مورا statement.
This one.
Is it there to eliminate? Yes. Is there to eliminate the recursion? No.
This one is an indicator that it's zero or more it's zero or more statements. So it's بحال regex. We say هنا بلي statements is one or zero or more statements. You let درنا plus it's one or more statements.
غير زعما واش زعما implicitly زعما does it eliminate هذيك infinite recursion حتى واحد الوقيته ما غادي يكون حتى شي حاجه and then غتحبس؟ لا.
Not necessarily في هذا الكيس.
Okay.
في هذا الكيس I think we did it more for clarity, and because we have different types of assignment, we have ممكن you can have if statement followed by assignment followed by if statement, and the easiest way to write it for grammar is to have everything as a set of statement, and one statement could either be if or assignment. This is just for an easier way to write it yourself.
All right.
But
thanks.
But you're right. In some cases you have to change your grammar to eliminate recursion. بحال كيف ما شفنا ديال left factor. Questions? No? Okay. I think we can do something fun now. We can see the good way to have a good way to visualize what we just saw. I don't know if you've heard of had software before, but Antler. So so you can visualize you can build your own grammar and evaluate it and debug it with examples. Antler, which is forgot what it stands for, but yeah, quickly. Yeah, another tool for language recognition. I see names. Anyway, so we did a similar thing in our case, our small language. Yeah, and yeah, it would be very helpful for the project to build grammar and see where there are problems, try to debug it, try to see if everything is all right. This is a very good tool actually to do that. And yeah, so as you can see, and again, the syntax is a bit different. It's fine. It does the same thing. So as you saw now, statements is one or more statements followed by an end of file. And if you remember, those are the keywords and operators and open and close parentheses and identifiers and literals that we defined last time. And now we define them to use them as terminals. Yes, so once you enter your grammar now, we have an if statement, which is if followed by expression, followed by then, followed by one or more statements, and else could exist, could be absent. So, and so on for every one of those. I don't know if it's clear the presentation, but yeah. So, for example, we can try to evaluate this expression. Well, we can try to build the syntax. We'll parse tree for this example. So we assign 1, then if x greater than 5, then x assign 0 to x, else assign 1 to x. We define the start root, which is the root of our grammar, if we remember correctly. And we click OK. And then we can see what happens. So the root evaluating two statements, yes, which is the first one. Then statement evaluates into one or more statements. Then there is an assignment. It understands that there is an assignment. The assignment is x on the left-hand side, and then the assignment sign, which is in this case assign, and then the expression on the right hand. What evaluates as expression on the right-hand side is a term, which is a factor, right? Because we have term. Expression could be a term or a term plus term, for example, or term minus term. The term is a factor. I evaluate in this case to a factor, which could be a literal, an expression inside parentheses, or an identifier. In this case, it's a literal because it's a number. So it evaluates to literal, which is 1. And it does the same thing for the rest of the code. Evaluates the other expressions. So at the end, we have this very nice representation, which is our parse tree. So we have root, which is one of a set of statements. Every statement can be, let's say, an assignment. X equals an expression, which could be a term, and so on. And it does the same for the rest of the code until it finds an end of file, which is the end of the input. Abdelrahman.
Can you visualize an example of an infinite left recursion using this software?
Yeah, I think I can try. I can try to do that. I think we can will not let me do that, but let's say statements is statements. Okay, statements. Oh, it broke it. Interesting. Let me see. Oh, there are a few errors in console. Oh yeah. Okay. Yeah. It returned an error. I think this is not a nice way to do it. Okay, let me think about it, and yeah, maybe I can try. I can try to come up with an example after this. But yes, I mean, if you write your grammar in an ambiguous way, you can result in infinite loops. Yeah, exactly. The tool detects blinking a problem, and then it refuses to execute. It throws an error when there is a problem like that. It also yeah, actually the tool is very interesting. You can see also the representation of every non-terminal that you have. You can see them now. For example, statements. You can see it tries to draw a flow chart ديال statements ولا state diagram ديال the statements which is one or more statements. Same for if statement could be one if statement or assignment. It's good. It's a good visual tool to see the states as well for the possible states for every non-terminal. Also, it tries to show you how it parses كل character to try to define. Yeah. So in case of regex and but yeah, very nice too. Okay. Any questions so far? Yeah. Name of this program? Yeah, another tool for language recognition. Antler. Actually, the UI is called Antler Works. So yeah, Antler I think is a command line tool. Yeah. Questions? Okay, so we can move on. Okay, so now that we talked about how to define grammar, now that we have defined the grammar, let's say, theoretically, let's see how we can use the set of rules that we have defined to parse the actual input. And the way we can do that is either top-down parsing or bottom-up parsing. We're going to see small examples. I'm gonna try not to dive into a lot of details. But top-down parsing is very similar to what we were doing in the example. So we start from the root of the parse tree, which is the start symbol, and we try to recursively construct the tree from the top. So we try to match the expressions from top to bottom. And then we expand the non-terminal into terminals, and then continue until we match every terminal symbol with its assignment. And this is exactly what we had here. So we started from, as you saw fluid, we started from root, then statements, then we knew that statements is one or more statements. We found some characters and then it evaluated into a statement. And then while parsing, we found out that there is a equal sign, so it matches assignment and so on. So it goes from top to bottom. And yeah, we will continue doing this operation until we find all terminal symbols that match their input string. So yeah, questions? Yes.
Can you please explain what you mean? But can you back to the slide اللي كانت قبل
Yes.
continue until terminal symbols match the input string. ما فهمتش هذا
Okay.
statement هذا شنو واش هذه.
Okay. هنا كاينين terminal symbols و non-terminal symbols. Yeah. Non-terminal symbols هما symbols that we are using في grammar. had statements. There is no such thing as statements في input string. ما تلقاش شي حاجة فيها statement ولا that evaluate to statement. A statement is something that we use to define the grammar. And this is what we call a non-terminal. A terminal اللي هو, let's say in this case, identifier. Identifier evaluates to a variable. Identifier غادي يكون x ولا in our case هنايا we have an identifier that is x. This is a terminal. A terminal في هذا example هو هاد identifier. This keyword identifier اللي كاينة في grammar, we call it a terminal because it's final. What's next after matching this identifier is matching it to a variable. Alors que non-terminals still have to be matched to one or more terminals. I'm not sure if terminals versus non-terminals is clear or not to everyone, but
Yeah, it's clear.
It's good that you mentioned that. Yeah, thanks for the question. Is it clear? Does this answer your question?
Yes, thanks.
Okay. Thanks. Other questions? Can she raise hand or a reaction? Okay. Yeah, so this is what we said. We said we start from the root, which is obviously a non-terminal, and we recursively construct the tree from top to bottom and then expand to non-terminals. And then those non-terminals, at the end, we should match them with their variables. With the keywords, with the parts of the input that they matched. Yeah, one technique is backtracking. Not very efficient, but it's one of the techniques. Yeah, so it's brute force. You try the one on the left, then you try the one on next to it, then you keep trying. If it doesn't match, you go back, you backtrack, you try to match the next one, and if you don't match anything, you roll back and you find an error. So this explores everything until a match is found, or you don't have any more options. And you can understand why this is very inefficient. For example, if your syntax is incorrect, the backtracking maybe would explore the whole grammar before saying that this is incorrect. So yeah, this is a very inefficient technique to implement a parse. Another way is called recursive descent parsing. So this is a better implementation. It's a predictive, more or less, approach. So it's also very easy. It's also easier to implement than other approaches. So in the parser, we implement functions that call each other based on the rules of the grammar, and we start from the root as well. So we start from the root, we implement functions in the code that match our non-terminals and terminals and production rules. Production rules are lines for grammar. Functions consume input symbols and backtrack if a mismatch occurs. There is a little bit of backtracking in this case, but it's less than trying blindly all the symbols. And yeah, by the way, I forgot to mention here, backtracking is where recursion or left recursion leads to infinite loops, because you're just trying the leftmost, then the right one, then the one on the right, then the one on the right. So nothing can add the most amount of backtracking actually. The most yeah. Now when left recursion would cause infinite loops. It may be also the case in recursive descent parsing, but yeah, it's a bit more efficient than, or it's more efficient, definitely more efficient than backtrack. So yeah, yeah, here it's easy to implement because it's close to the grammar. We implement one function. I mean, a good practice is to implement one function per non-terminal. So for example, and now statements. We're gonna have a parse function for statements, parse statements, and these parse statements will call, for example, parse statement, which we'll call parse if statement. Parse if statement will check if the if expression is good, if it matches. If so, it will also call parse expression and so on. So it's a bunch of yeah, functions yeah, calling each other. Very close to the way that we define our grammar. Yeah. Now we can talk about conditions that we need to have a grammar. Before we can use recursive descent parsing. So one of the conditions, as we talked, it should not be left recursive, and it should be left factored. I think we talked about the left recursive and left factoring. Yeah. So before you implement usually top-down approaches, recursive, and one of them is recursive descent. It should not be left recursive, and it should not be, and it should be also left. It should be left factored. Yeah. So one more thing here, the Go programming language uses this recursive descent parsing to parse. Yeah. Actually, it uses a combination of two parsing methods, but yeah, recursive descent parsing is used as well. Yeah, LLK parsing, I think I won't go into much detail because you know have a lot of time, and also yeah, it's a bit complicated for yeah, for the sake of this presentation. So yeah, LLK parsing is a type of predictive parsing. So it comes up with a technique that tries to look further ahead in the input to try to predict the part of the grammar to use for every kind of expression. So let's say, yeah, LL, by the way, stands for left to right, leftmost derivation. And it tries to predict the symbols to use, or it tries to predict the parts of the grammar to use based on the parsing decisions that we have. And yeah, it looks at the input symbol to decide the production rule. Usually LLK, K means the number of symbols to look ahead in the future, or to look ahead. And yeah, it looks at the current input symbol to decide production rule. It also constructs a parse table based on those rules to determine the rule to use in every case. And yeah, this is an attempt to try to avoid backtracking. So given this example, this is a very basic example. I think LLK parsing would be would be better understood with multiple examples, but yeah, just for the sake of time. Yeah. So here A evaluates into A, B, or B, and then B evaluates into C. Or yeah, B is a non-terminal that is C. So in this example, the LLK or LL1 in our case constructs a parse table based on first and follow. First and follow are functions that are applied on the grammar to try to finds the first occurrence or the first terminal that appears in a certain expression. For example, A is A, B, or B. The first thing that appears in this, the leftmost thing that appears in this expression is A. So this is first. And follow is the next one that appears after this expression. So after A, there is nothing. So follow is nothing. After B, there's also nothing. AB is not followed by anything. So for example, if we had here ABC, the follow of B would be C. And then based on those first and follow, we define intersections, or we define cross intersections between non-terminals and terminals. And then we take the input, we put the input in a buffer, and then we start reading from the input. If we find one terminal, we know that we're trying to predict the next grammar rule that we are going to use, so that we don't fall within in cases of backtracking. And this is the idea here. I'm trying to explain this in a very broad way, but yeah, I hope the intention or the idea is clear. Questions? Okay. Yeah. Other ways of parsing is bottom-up parsing. So one common bottom-up parsing algorithm is shift reduce, LRK, handle LRK parsing and handle pruning. For the because we're running out of time as well, so we're only gonna talk about shift reduce. So bottom-up parsing does the opposite. It doesn't try to match things to the root, top down parsing, but no, it tries to start from terminals and make its way up to the root. So it does this by applying two operations, shift and reduce. So those two operations are shift operation and reduce operation. So it has a buffer and a stack. So shift moves the cursor from the buffer to the stack. It tries to append, or it appends tokens to the stack, and then it reads the stack. If you find in the stack that there is an operation that can be reduced into a non-terminal, you replace it with its non-terminal. Let's try to have an example here. Let's say we have if x equals 5, then let's just take if x equals 5. So if is added, x is also added, and then we're trying to reduce. There is nothing that is if something. There is if something, then something. So we keep adding until it matches one of the statements we have here. So if x equals 5, then set x to 1. If x equals 5, the expression x equals 5 would evaluate. So x is an identifier equals, or yeah, let's say equals could be here in an expression. If x equals 5, so x equals 5 would evaluate into an expression. So we would substitute x equals 5, which we have in the stack, with expression. And now we have if expression in the stack. Then we add then, and we add the other side. And the other side would evaluate into statements. And now we have if expression, then statements, and then we reduce into if statement. This is how it tries to apply this. So it tries to apply it bottom up. Tries to match the stack, everything that it has in the stack, to the grammar. If it finds the matches, it reduces. Otherwise, it keeps shifting. And these are the two operations. Shifting is basically moving to the stack from the buffer. Reducing is popping from the stack everything that could be reduced with the non-terminal. I hope this makes sense. Questions? Okay, so this is what we said. Shift and reduce, initialize the stack with the start symbol, repeat until the stack contains only the start symbol and the input is empty. If the top of the stack matches a production rule, perform a reduce operation, otherwise perform a shift. So if the start only contains the stack only contains the start symbol, it means we are done. If something is staying there, it means we faced an error. And if there's no operation that can be performed, there's also an error. Okay, so we are moving to the implementation. Yeah. Not sure if there is. Okay. Yeah, we can try to just to go through the code. Okay. So last time we implemented the Elixir, right? So Elixir with with next token. I mean, yeah, that was the assignment for last week, right? So we implement Elixir that takes an input, that takes the source code as an input, and then defines or generates tokens from them, and then outputs a list of tokens. For the sake of knowing that we are done, I added an end of file type. I think I can find it in the token. Yeah, just end of file. Then left parenthesis, right parenthesis. And then the Elixir now is just using next token, returning token. Okay, now how can we use this Elixir? So one way is just to include it in our parser. And yeah, Elixir just takes this and then the parser tries to parse. So Elixir calls the parser calls the Elixir next token, keeps searching for tokens, and then it appends to just this list of token, and then at the end it breaks. Yeah, just for now. And then it calls parse statements. As you can see here, I tried to stay very close to the grammar. I don't know if you remember, but the top level or the root was statements. This is parse statements. And yeah, this is the setting the node. I mean, yeah, I'm going for this a linked list like data structure. It has like a root and children. So yeah, generating these statement nodes, and then for every token it tries to parse statement, and for every statement it tries to add those as children, and then return in the node for statements when everything is done. Zooming in into parse statement, we're gonna find something very similar again to the grammar. If the type is keyword and it's if, return parse if statements. I'm not sure if you are following with the. I mean, you're remembering the grammar, but this is how it looks. And the code looks very similar to what the grammar is trying to describe here. So parse statements is one or more, or here 0 or more statements. It's the top level. Statement is either an if statement or an assignment. Trying to do similar thing here. So it's an either it's an if statement or it's an assignment. This is a statement. And an if statement is trying to parse the expression. And if, let's say, I mean, here trying to match the then to see if there is a then keyword or not. And then, tries to parse the then block, which could be one or more statements. And then it tries to find the else block. And then once everything is done, it returns it. And then if we zoom in again and so on, I think it looks very I think it's very simple to make sense out of this, or to link it to the grammar, because it's very representative of the grammar. This is why I said it's the recursive descent parser is pretty easy to understand when you read the code and look at the grammar. Questions so far? Okay. Questions in general for parsing or syntax analysis in general?
Like any good practices or things to avoid when we're writing our own parser? Things
Sorry?
things to avoid doing when writing our own parser.
I think there is. I would say there is. I think it's a twofold job. It's defining the grammar, then using the grammar to build the parser, then trying to follow the rules of the grammar to build the parser. So I would say defining a simple. Sometimes you can see that in especially in cases of or examples of programming languages, or real production parsers, you can see that sometimes they're very exhaustive or very they don't try to factor in everything. They try to be explicit while they try to define where they try to define, let's say, tokens ولا statements ولا حتى non-terminals, so that you don't leave a lot of room for error. But this is for the sake of just learning, I would say just define a simple grammar. Try to for our sake, we just try to do it, and then it will. You will try to find challenge. You will start to find challenges as you go into more complexity. And precedence is one of the problems. Let's say you have two statements which have the same order of priority, ولكن logically they should have different orders of priority بحال multiplication مع plus. And in other cases you can have a problem when your grammar is not trying to put the precedence into account as well. So you either fix it on the grammar level or you try to introduce something on the code level that tries to fix this problem. And I think in Go they use a kind of a mixed approach between recursive descent parser or shift and reduce, I think, for operator or for operation. What is it called? Yeah, operator precedence parsing, which is a bottom-up approach باش يsolve غير the operator part at least, ولا some of the arithmetic operations. But this is programming language level. I mean, this is complex production programming language level. For our case, I think it's just learning. Yeah, Mehdi.
Yeah, I think if you go back to the tool that you showed us, I think هاد المشكلة اللي دويت عليه وقيلا كاين تما because we prioritize plus before multiplication division, right?
Okay. Yeah.
I think this is like
exactly.
Yeah, it should be the opposite.
Yeah, exactly. I mean, actually no, because we're seeing it from top down. We're considering expression as a sum of factors, and the factor could be a multiplication of terms. Well, sorry, expression as a sum of terms, and a term could be a multiplication of factors. Okay, priority is correct here. It's the multiply. Because
إذا ما احتاج
sorry.
إذا ما احتاج it's evaluated هي الأخرى multiplication داكشي علاش.
Exactly, yeah, because احنا شفناها من top down. شفنا expression هي الأولى هي top level.
ولكن كتمشي من left to right.
Exactly. Okay. Yeah, I mean, this is the sum of terms, and the terms are products. Donc products غادي تحسبوهم الأولين when we're actually doing the computation.
Can you try it? Like for example, 1 plus 2 multiplied just to see it, the amount visually, maybe.
Yes, 1 plus 2 multiplied by 3, right? Let's do this. Yeah, you see, this is, I think, yeah, so it's 1.
Yeah, exactly.
Yeah. 2 times 3 is 1 term, which are 2 factors. وهنا 1 term evaluates to 1 factor.
Makes sense.
Cool.
Okay, thanks.
Yeah, thanks for the question. Anything else? Okay. So, yeah. Assignment time, I would say. But anyway, I think the logical extension of the work did last week is to build, or to make your own parser now. I would say try to use recursive descent because it's the easiest. Yes, exercises to build the parser, exactly. Exercises to build the parser using the lexer that you already built. Try to define a simple grammar first. It would be nice. It would be nice to have a, let's say, a doc, a text file to refer to when you're making your parser as a spec for the grammar. So define the grammar and make your own parser. That's the exercise. I will try to build. Will try to define some tests. But I think it would be nice to, if you want to read more about the other ways or the other techniques or other algorithms deal parsing. It's a good thing to do, Hamid. And it's also, I mean, if you're curious to know more about different ways to build a parser, you can explore the algorithms and choose, and then define your grammar and build your parser. Otherwise, you can use the case of the example I used, the recursive descent. Okay. Yeah, I'll try to have some test cases. Yeah, and then push them similar to the format that we did last week, and maybe also a little bit of description. I mean, I don't know. I don't know what cheating is in this context. If you're using it for learning, I think it will be fine. But I think it's in this way. I think it's easy. It's easy to just do it from scratch. I think it's it's fun. It's a fun experiment. Yeah, Yaka I think is a parser from, you give it the grammar and it gives you it generates the parser, right? Yeah. Okay. Cool. Assignment. How was the assignment submitted last time? If I remember correctly, it was this semester. Yeah, I think it was not mentioned last time, but I think the exercises are not submitted. I mean, the exercises are not submitted. You do it for yourself, and if you need help or you want to share it with us for to have a small look, then you can do that. I think the project is what you can share with us in the end. But interface? Which interface? Red? Ah, I think it's the old server Nizar, yeah.
لا صيفط سيرفر جديد. غتلقى الميساج درت ليه كوبي كولي جو
Perfect.
بونس
Okay,
هو السيمانة صيفطو.
ça marche. Yeah, thanks Nizar. Okay. I think that's it.
Abdelghafour,
Yes.
is there any way you can ping زعما مهدي باش يأكسبتي واحد الدري من قبيله هو كيحاول يجوين؟
I'm not sure if Mehdi is reachable right now.
Yeah.
ولكن
اوكي راه قبيله هو كيهضر في ديسكورد شويه.
كون admin. I'm not sure.
مهدي غالبا.